Alright, so here in section 4.7 we'll be talking about the inverse trigonometric functions. Now first of all, we already know about the inverse functions, right? Now can you tell me one single property that we can use to identify the inverse, identify for a function that whether an inverse function exists or not, just looking at the graph? What was that? There was a test, remember? There was a test by which we know that if we do the test on a graph, we can tell that whether that graph has an inverse or not. What was that test? It was a simple test. Remember, we did it in the inverse function. There was a section in chapter 1, which is extremely related to this one, because we are just talking about the inverse trigonometric functions. But there that was what test? Horizontal line test. If you can draw a horizontal line such that it intersects a graph at more than one point, that means that graph does not have any inverse. If you can draw a horizontal line such that it intersects the graph at more than one point, right? That was a simple test, but but what do you think? If you recall all the graphs you have for the trigonometric functions, do you think that they have inverse? Look, think about the sine graph. Can you draw a vertical line which can intersect that graph at multiple points? Of course you can. Think about the sine graph. Interesting is, think any trigonometric, because why it happens? Because trigonometric functions are periodic functions. Same things are repeated. So you should be able to draw vertical lines which will be intersecting those trigonometric functions at infinite number of points. For an example, let's look at the sine graph. How the sine graph look like? This is the sine, right? Look at this. You can draw plenty of lines that intersect at more than 2 points. So now the question is more interesting. So why we still have some inverse trigonometric functions then? Because none of the trigonometric functions should have inverse in that sense. Because by the definition of, or by the test, we don't have it. Now the interesting is, which is true, that the trigonometric functions do not have inverse theoretically, but what we do is we restrict the trigonometric functions. For an example, we can restrict the functions, right? We can remember in one section of chapter 1 we were talking about the piecewise function. Remember that part? That function can be defined only for a small range or domains. Remember that one? We are exactly doing the similar thing here. We are trying to restrict the function. We are just saying that, let's say we have a sine x function which is y equal to sine x. But let's say we define the function only between this range, which is negative pi by 2 to positive pi by 2. Now the function will look like only this, right? Because we are restricting. We are not saying that the function is infinite. In general, that graph is infinite, right? It goes all the way to positive infinity and negative infinity, but we restrict the function. Now the function look like only this. Now at this point, this function has inverse, because this is only the graph, and you cannot draw one line such that it intersects the function or the graph at more than 1 point. You see it, right? Can you draw more than one line? Can you draw any line such that it intersects the horizontal line such that it can intersect the graph at more than 1 point? So this is how all the inverse trigonometric functions are defined, because they are restricted. They are defined only for this range, and then it has an inverse. Because I just wanted to make sure, because we understand that, okay, we understand
why some function or some functions the inverse function exists. By that definition of the horizontal test, we know that none of the trigonometric functions should have inverse functions. But since they are restricted, okay, we can restrict them and then we can define their inverse functions. You know, the picture 1, you see that horizontal line which is intersecting the original sine graph at more than one point. It will be basically infinite number of points where you will have that intersections. Now, just to make sure, I think we already have talked about this when we are discussing the inverse function. The inverse function doesn't mean this. It does not mean that y equals to 1 over sine x. Okay? Because y equals to 1 over sine x means we write it using this format, that sine whole to the power minus 1. But the inverse function is written as sine inverse x. So inverse function is not reciprocal function. Okay? This is a reciprocal function, that y equals to 1 over sine x. But the inverse function is not that. Again, I think it was we already mentioned it in general, in every inverse function. This is what we do, and we already mentioned it in the inverse functions when we are discussing the inverse functions in chapter 1. So, if you are taking the reciprocal of sine, you will always come up with cosec, because the sine and cosec are reciprocals to each other. So this is the formal definition of inverse sine function. Now how you are going to define it? Again, as I said, the original sine function is defined within this range, that x is going to be within negative 90 to positive 90. If that is true, that inverse function means sine y equals to y. So again, think about this, that any sine function, what it does, it takes the angle, right, and it gives you the ratio, right? Think about the original sine function. What it does, it takes an angle. Let's say you give 30 degree, and it gives you 0.5, because it's basically doing some kind of ratio calculation, right? And it gives you the ratio of two sides of the right triangle, right? So it takes the angle and it gives you the ratio. Now the inverse function does the reverse. It takes the ratio and it will tell you the angle. For an example, if you just give it 1 for sine, let's say what is, for an example, let's say what is sine inverse of 1. Let's say if you're trying to find sine inverse of 1. So that means you are asking that for which angle sine becomes 1. What is that angle? 90 degree, right? For sine 90 is 1. It's going to be pi by 2. So, you know, I'm just trying to show you that what basically the inverse function does. It basically gives you the reverse. It takes the ratio, it gives you the angle. Okay. So, as you can see from here, we are trying to draw the inverse function. If you look at this graph here, the red line is the sine graph. So, in this whole section, you will see the sine function just like this, because we are always drawing the sine function within that restricted domain from negative pi by 2 to positive pi by 2. We'll not be drawing the sinusoidal curve, because we know that for that there is no inverse function exist. Now the red line is the original line and the blue line is the inverse of that. And as you remember, I think you can recall from the inverse function section, remember any function and its inverse are reflected about y equal to x line. Remember that? If you draw a line y equal to x, what does it mean? For that line, every point has the same x, same y. See, something like 1, 1, 2, 2, 3, 3, 4, 4, negative 1, negative 1, negative 1, negative 2. I'm sorry, negative 2, negative 2. Those are the points on that line. Okay, that line is the green line. Do you see the green line there? So any function and its inverse function are symmetric or reflected about that line, and which is again the common characteristics of every inverse function, which is also true here. So this is nothing different. This is nothing new. This is no characteristics of any inverse function, which is also true for the sine. We just wanted to make sure that you have the common properties of everything.
Now here, we are just trying to show you that, okay, now, let's say these are the angles. And for those angles, these are the values of the sine. Now, how the sine inverse function works? What do? You first assume that theta equals to sine inverse x, because theta denotes an angle in general. In general, we use the Greek symbol theta to represent any angle. So that's why we write theta equals to sine inverse x. And then, because you know that the sine inverse x will be giving you some kind of angle, which will be, again, within this limit, because the function is always defined within negative 90 to positive 90. So whatever the value you will get, you will always get something between negative 90 to positive 90. Now, to get the exact value, so we use this table, because this table is we have all the common angles and their values. Common ones like 30 degree, 60 degree, 90 degree, those things, and the negative ones, the negative 30, negative 60, negative 90. Okay. So you see here, this is the negative 90 all the way to the positive 90. And these are the values. Now let's see how you can find 0 from here. Sine inverse 0. All you need to do is just find the 0, ratio 0 from here. What is the ratio 0? Here, right? What is the angle for that? 0. Now let's see sine inverse negative 1. How to find that? If you try to find the negative 1 here, here's the negative 1, right? So what will be the angle? Negative pi by 2. It's so simple, because you just look at here, negative 1, whatever the ratio you are given, for that just find the angle. Okay? But you know, these are the common angles. There are other angles too, like 37.5 degree. You will need the calculator for those. I'm saying you can still find the ratio for those. But doesn't matter what it is, your angle, because the inverse function is defined only within this range, your angle must be between minus 90 to positive 90. Okay. Now let's see. These are again the same kind of thing. So again, it's about the cosine. Again, we just have the same situation here. The cosine function is also restricted, because the original cosine function does not have any inverse. So when it is restricted, and the only difference is, look at the difference in the restriction. Now the sine was restricted between negative 90 to positive 90, and the cosine is restricted between 0 to pi. Do you see the 0 to pi here? So this is 0, right? And this is pi. So 0 to pi, the red line is your cosine. So that's how this is going to be the inverse cosine of that. So the blue line. And similarly, we have the angles starting from 0 to pi, and these are the common angles. 30 degree, 45, 60, 90, 120, 50, 60. Just all the common ones, like 100, it's all the way up to 180. Okay. And when you are finding the inverse, all you need to do is just look at negative 1 there, and go back here. This is negative 1. So your angle must be pi. Let's say this is square root over 2 by 2. What is this? Square root over by 2 is this. So the angle must be 45, pi by 4. And remember, uncommon angles, we use the calculator, because these are the common angles. This is for the tangent. I'm just going a little bit quick, because it's pretty much similar information. And we restricted this, but look at one important thing in the restriction. We are restricting it between negative 90 to positive 90, but look at the restriction. There is no equal sign. Remember the previous restriction, we wrote like smaller equal, but there is no equal sign. Do you see it?
does anyone have any idea that why there is no equal sign? Because at negative 90 or positive 90, tangent is undefined. So you cannot include that point. That's why we just wrote greater than this, smaller than this, but those points are not included. Okay, that's why you see you know that, right? That when you have the parentheses, those points are not included, right? Just that's how we write the domain and range, right? So exactly. So this is the inverse function, which is symmetric about y equal to x. Same situation here. So these are the points, and we can find their. So these are the three trigonometric functions so far we covered: sine, cosine, and the tangent. So and again, using the tables, we can find all of these. So here is some info for you that how you can find the other angles, because you
have to find the other angles too. How you can find the other angles using the graphing calculator, the one we have. So look at the slide and see whether you understand it. But remember, before you start, you must have to change the mode into radian mode. In general, the default mode is degree. So check whether you have the radian mode set, and then check the. I think this is extremely simple. Once you have it, it's extremely simple. And see the examples how you can write 1/4. You can just write 1 divided by 4, and then see whether you can get the values. Do you have the answer? Did you check? Anyone has any trouble? All right. So if not, so you can try this problem, and then so let's stop here. Just try a couple of these questions, and we'll stop here. And then next class we'll have like a couple of more slides for this section. We'll finish those 2 or 3 slides, and then we'll go to the next section, which is section 1.8, and that is going to be the last section for chapter 4. Just let's see.